Okay, welcome back everybody. Happy Friday. Today, September 16th, it is our 5th class. We are covering 2 sections in your book. First one, we're going to cover something called the derivative function. That word hopefully sounds familiar. Derivative is what we introduced last class. Today, we're going to go from derivatives specifically at points to the derivative thought of as a function, much more general. And then the other topic is something called differentiability, the ability to take a derivative of something. Again, coming up, we've got quiz number 1. I will tell you more about that as we get closer. I'll tell you about that next week. Hopefully still making good progress, slow but steady progress on the 2 projects, arbitration and trucks. Yeah, Jim? There is not a practice quiz. The quiz, I'll say more about this next week, but the quiz is a take-home quiz, and it is open packet, and it is calculator active, but it is not, there's no practice quiz per se. Yeah, Lex.
So the quiz, I'm sorry, you just said it was that's the same day.
I'm gonna give you the quiz on September 21st, Wednesday, and then you're gonna take it home, do it Wednesday night, and bring it in Friday morning. Okay. Yeah, Rich. Okay. Yeah, I'll give it to you Wednesday. You'll give it to me on Friday. Okay. Other questions? Yeah, the project check-in day, I have no agenda. We're just going to come in Friday, a week from today, and you're going to work with each other on the projects. And if the people at your table are not in roughly the same place on the project that you want to work on, you'll find somebody else in the room that is. And you've got each other to work with, and you've got me. I'm happy to answer questions on that day. I'm just going to walk around and sit up here. I'll probably have some grading with me, and I'm happy to help on that day. But again, you want to come into that day as far into the projects as possible. If you really haven't gotten very far and the people at your table are like 4 questions ahead of you, they're not likely to want to spend their time catching you up to where they are. Okay? So do as much as you can ahead of time. Mahendra. I don't remember. The quiz, I think, is just 1 page front and back, but I don't remember. There's like a recommended time limit of like 24 minutes or so, but there's no official time limit. So about 24 minutes. Okay. Other questions? All right, lots of good questions. Thank you for that. So again, starting on page 31 with our daily summary. In this class, we sketch the graph of the derivative of a function with a given graph. We also explore what kinds of things make a function non-differentiable, whatever that means. So we'll start with our first demo. This is going to be a little bit unusual today because I'll do 2 demos and 2 activities. In the last section, we defined the derivative of the function f at x equals a to b, and then we had this crazy looking formula. And so I'm hoping that the more we look at that, the more the pieces start to click, and we've got this visual in our minds. This fraction right here represents the slope of a secant line at a particular value of x. In this case, it's a is our generic number for the input variable. And the slope of the secant line becomes the slope of a tangent line when we send h to 0. And so again, this is the visual I'm hoping we're starting to develop, is this horizontal distance compressing. So secant lines become tangent line. Yeah.
Does it become the tangent line as soon as you get it like really close to 0, or because a lot of times once you get it to 0, you just get an error?
Yeah, and so you're not allowed to just type the 0 into the calculator because you get this error, but technically it is not the tangent line until we talk about the limit, which means making h infinitely close to but not equal to 0. So you're not allowed to say, oh, if I'm at h equals 0.00001, that's the tangent line. It's not. It is still a secant line, which is almost smack on top of the tangent line, but technically infinitely close to 0 is what we're after before it becomes the tangent line. Okay. So we talked about the slope of a tangent line at a particular point, but maybe we can think about the slope of the tangent line at every point and think about that as a new function. So only difference here between 1 and 2. This thing right here is the derivative at a specific number a. This thing right here is the derivative at a generic x. And so what we're going to do is try to apply this new idea of the derivative function by graphing it. 3. Let's see if we can take the graph of y equals f of x pictured below, that's the one on the left, and sketch the graph of f of x on the right. Probably should have put a y equals in here. Maybe put a y equals in front of that thing. Y equals f of x is what we're sketching. And so the idea here is that for each input value, we've got an x, and we are going to plot on the y-axis the f prime, the slope of the tangent line. That's what it says here. We are plotting points of this form, x, comma, slope, slope of the tangent line. So let's take a look at the given graph. I'm going to first key in on the tangent lines that are horizontal. Can you put a dot on the first graph on any point with a horizontal tangent line? So we've got a few of them. Put dots on any point on this first graph with a horizontal tangent line. Yeah, Ren? Yes? Inflection point's a different thing. Critical points is what we called them on the first day. Yeah, those, right? We got maxes where it changes, increasing to decreasing, or decreasing to increasing. So in this case, hopefully we see that there are 3 of them, right? 3 places with a horizontal tangent line. I am also going to put some dots at some other points, just sort of random points that are roughly in between these. And so I'm just going to pick a point here. Doesn't have to be like any particular one, just a representative point, something there, something in between here. And how about we pick ones on the far right and far left as well? Okay. You know, as I did that, I actually want to be a tiny bit more precise than that. I'm going to pick points that are at integer values. So I'm picking one at -2. And let's go ahead and pick this one here at the origin. And let's pick one at 2. And then we'll pick this one up here at 4. Just make it easier for us to plot on the right. Okay, and now we are going to think about tangent lines, because after all, we are graphing x, comma, slope, slope of the tangent line. So we said that at this first orangish point over here, tangent line is what? Has a slope of 0. And the same thing is true at the other points where the graph is flat. And so if I am plotting the point x, comma, slope, how much is the x for this far left orange point? It is -1. And how much is the slope? 0. And so over here, I'm going to plot a point at -1, 0. See it? X is still x. But y is not y anymore. Y is the slope of that particular tangent line. Can you go ahead and put, can you plot on the right-hand side the points corresponding to the other 2 orange points that I've got here? The other 2 flat points. All right, so Jim estimated about 1.4 there, comma, 0, that's good. And then the last one? 3, 0, good. And so go ahead and plot your 3 points, all of which have a horizontal tangent line, which means the slope is 0. So 0 becomes the y coordinate on this new graph. And then I'm going to draw again some green tangent lines. And I'm going to draw these tangent lines at my blue points. And so just a very quick tangent line. This is like kind of a rough and dirty thing that we're doing here. Something like that. So I've got 4 more tangent lines, 4 slopes to approximate. And we don't even need to sit here counting boxes. This is just a very rough sketch. But the first slope that I've drawn, the far left-hand one, it is a steep downhill line. Steep and downhill means what kind of a number? Negative and pretty big, right? Like not too close to 0. So I heard -3. Are we willing to say -3? -6 is okay. -3 is okay. Just anything fairly big and negative. Okay, so let's plot. Let's go back to purple here. How much is the x at that first blue point? -2. My axes only go to -4. So I'm going to take your first answer, which was -3. So the x is still x, but the y is the slope of that tangent line, which we just ballpark at -3. And so we come over here to the other graph and we plot -2, -3, and there it is. I've got 3 more tangent lines to approximate their slope. How about this one at the origin? Maybe 2. That seems good. It's uphill, not quite as steep as the downhill one we just did. How about the next blue point, the third one here? -2. That seems good to me. To me, that looks kind of like a -1, but it's all approximations. So it doesn't have to be perfect, and we're not all going to agree with each other. And then the last one here at the far right, 3 is good. Uphill, pretty steep, pretty big. 2.5 is okay. All right, and then we plot these other points. So for this point right here, x is 0, and the y value we're plotting is 2. So we put a point at 0, 2. 0, 2 up there. And then the next point we're looking at is this one here. X is 2, and y is -2. 2, -2 down there. And then I think we just got one more, this guy right here. X is 4, and y is 3. 4, 3. 4, 3, right there. And so we've got 7 different points, and you're just going to connect them in some fashion. So let's draw here in blue. So we're connecting these points. And we're missing those points, so we're going to try again. Connect the points, something like that. And then we turn around someplace, maybe like that. Is it possible that the graph came down a little bit farther, that it hit my point at 2? It hit my point at 2 and kept going down before turning around? Is that possible? Yeah, don't be deceived into thinking that the points you picked were the highest and lowest points. We just sort of picked some kind of randomish points in between, okay? What that means is that there's a lot of flexibility in terms of getting full credit for your answers to this kind of problem. Graph just has to look generally like that, but it's not going to be exact. Questions on that? Yeah, Matt. Lex, how'd you get -3?
Because I did a really rough estimate, just the negative slope. I realized it was the opposite. Yeah, just kind of like ran it into where it would hit the next unit over the slope.
Yeah, so just draw the line a little long enough so that you can actually literally count boxes and say, oh, like maybe we go from this point and then we go over 1 and down 3 to land back on the tangent line. And so you're literally just thinking about change in y over change in x and just counting boxes. The m equals 2 here? Yeah, so this guy, if we draw it a little bit longer, maybe something like that. Your job is to just pick points that you think are roughly on that graph. And so, for example, this point right here looks like it's on the tangent line, and I guess the origin is on that tangent line. And so we count boxes just thinking about those 2 points. So how much is the rise? 3, and the run? 2, so the slope is 3/2, which is 1.5. Somebody just guessed 2. My estimate there is slightly different, but still positive and fairly close. Yeah, all approximations there. Okay. Number 4, to reiterate, when graphing the derivative, let's label this guy just to be super clear. This is the graph of what function? F prime of x. That is the graph of the derivative function. The apostrophe, we read it as prime, and it stands for the derivative. And in the homework that you guys did and showed me today, you found like f prime of 2, and you found f prime of 5, and you estimated the derivative at particular values. So the new thing for today is that we're saying, oh, but the derivative at particular values means that maybe we can think of the derivative at all values and just get a brand new function from the original function. anything we do with the graph is an estimate. We will have rules that, that tell us if you know the formula for the original function, you can come up with the formula, and that's going to be exact. We'll get there. But anything with the graph is approximate. Okay, so yeah, we got that. So the x value is the input, and the slope of the tangent line at that x value is the output. Based on the graphs above, let's guess the degree of f, which was the original. Hold up the number of fingers. What degree would you estimate for the original graph? Let's see a few fingers. I want to see more fingers. More fingers. So I see lots of 4s and a couple of folks not quite sure. So the people holding up 4, how do we get 4? 3 turning points, right? We got a min and a max and then a min. And maybe some of us know that, yeah, it's like the degree is typically 1 more than the number of turning points. Okay, great. So we think maybe the first function is a degree 4. How about the degree of f prime? Yeah, that looks like a cubic to me, right? It goes up and then it comes down and it goes up. And that's what a lot of cubics that I know do. So that one looks like a3. And we will soon see that for any polynomial only, f of x, the degree of f prime, how does it relate to the degree of the original? Guesses? Yeah, 1 less. 1 less. That's true. For any polynomial, the degree of the derivative is 1 less than the degree of the original. Okay, so like I said, a little bit unusual today in that we're going to have 2 demos and 2 activities. So you are going to start this activity and get as far as you can. And with about half an hour left in our class, so about 9:20, I'm going to call us back together. We'll do another demo, and then you'll do more activities. Go ahead. Everybody come back. Okay, we are jumping to this demo right here. It's on page 36. 36. Okay, here's a keyword for us. We saw it last class. If a function has a derivative, then we say that function is differentiable, meaning if its derivative exists. Now that derivative is a limit, and we know that limits can fail to exist if you get different numbers, say, from the left and from the right. Remember we talked about limits a few classes ago. And so there are a few basic ways for a derivative to fail to exist. First way right here is that picture with a corner. If you are thinking about slopes of tangent lines, you know, like at this point right here, there's a tangent line, and at this point, there's a tangent line. And if you come in, there's a quote-unquote last tangent line coming from the left-hand side, yeah? And if we go the other side, I'm actually going to draw that last one in blue from that side. And then if we go the other side, you know, here it's got a tangent line, and here it's got a tangent line, and then there's kind of a last tangent line from the left-hand side, yes? Now we know that limits, for a limit to exist, you got to get the same number as you approach from both sides, right? And if you end up with different numbers from the left and the right, then the limit doesn't exist. Quick sketch, like there and there. The limit at this number does not exist, right? Because from the left it's one thing and from the right it's something else. And so that's what's going on here. The limit, these tangent lines all have slopes, and the slopes from the left are some positive number. They're approaching some positive slope, whatever the slope of that last blue tangent line is. But the slopes of these guys from the left are negative numbers, and the last green one is some negative number, and for sure the green one and the blue one do not have the same slope. And so I'm imagining this picture over here up in the top right is that just got 2 different numbers at that one spot. And so if you have a corner, it doesn't have a derivative. It doesn't have a tangent line. If it had a tangent line, there would just be a single line that we would all draw and say, oh yeah, that's the tangent line. But we can't, right? Imagine trying to draw a tangent line at that point, at that corner. We can't. Another place where the derivative doesn't exist is a spot where you have a vertical tangent line. So for example, right there, if I were to draw my tangent line at that spot, it would be straight up and down. What can you say about the slope of a vertical line? Is it 0? It's undefined. It doesn't exist. And so The derivative, which is the slope of the tangent line, does not exist if you have a vertical tangent line. You can still talk about it. And it has a tangent line, for sure. I've just drawn the tangent line. It's not that it doesn't have a tangent line. It's that the derivative doesn't exist because the slope of a vertical line doesn't exist. It's undefined. And then the last one, this is kind of a tricky one here. Last one is any point of discontinuity. It feels like this graph has a tangent line at that hole, doesn't it? Can you imagine the tangent line at the hole? Right? You'd have no trouble drawing it. You're not bothered by the fact that there's a hole there. And so if we all agree that that's the tangent line at the hole and it has a slope, then it sure feels like the derivative is going to exist. Not going to get into the technical details of why it doesn't work, but you can think about it later if you want. You can ask me about it later if you want. I'm just going to say, if the function has a discontinuity, it does not have a derivative at that spot.
Just at that point.
Just at that point. Every other point on that parabola is looking good.
And is that true for the other graph too? Like every other
Every other point. Yeah, there's only 3 places in this whole picture, the set of pictures, where the derivative doesn't exist. It's those 3 points. Lex?
Saying that if they come like the corner, they're coming at separate slopes. Set.
Yep. No, these guys are okay, right? Yeah, at x equals 2. That's the problem. Wait, at x equals 2? Oh, yeah, gotcha. Yeah, so Lex is saying if we look at this point right here, then the slopes from the left-hand side are all negative numbers. Everybody agree? And then the slopes from the right-hand side are all positive numbers. Does that mean that the derivative doesn't exist at the bottom? No, why is this the only one where that's okay? Josh? Towards what number? Towards being 0, exactly. So the only place where there's no problem having negatives and positives is if they happen to be honing in on the single number 0, which is the dividing line between the negatives and positives. But that was different for the first picture. Yeah, well, I don't know they were infinity. I mean, like one is approaching 1 and the other is approaching -1 or something like that. Yeah, good question. Okay, number 2. Let's identify all points of non-differentiability, places where the function does not have a derivative. Okay, what's the issue with this first picture? It's not continuous. So any point where the graph is not continuous, it's not differentiable. So points of non-differentiability here, x equals, start naming some numbers where the graph is not continuous. -1, 0, 1, 2. Whole numbers are 0 and positive, so it's integers is the word we want. Yeah. So this guy is not differentiable at any integer. But at all the other numbers, no problem. What's the derivative of this function at 2.4? 0. Tangent lines for all other points are horizontal. Okay, part B, the function here is the 5th root of x. What's the one problem here? It's an undefined slope. So x equals what number is the bad one? 0 in this case. Derivative is not defined there. Okay, this one I think we have a little bit of work to do, so we'll draw a quick sketch of this piecewise function. So on the one hand, we're drawing x until we get to 3. So y equals x until we get to 3. So that means I'm going to put a circle at 3, 3, and then draw that 45-degree line that way. Everybody okay with that? And then the other one is also a line, right? 2x minus 3 is just a steeper line. The slope is 2. Y-intercept is -3. So I'm gonna draw the line, but then I have to erase it and draw it right. So the y-intercept is how much? -3, which unfortunately is off the picture. And then the slope is 2, right? So we go like over 1 up 2, over 1 up 2, over 1 up 2. I guess what I really need to know, like it looks like it's kind of close to the point with the circle in it. I need to know really what's going on there. And so maybe that's the place to start, is to plug in, how about we do plugging 3 in for this x. What do we get? We get 3. So that means that the point that we just found is what? 3, 3. Everybody agree? 3, 3. Okay, so 3, 3 actually fills in that empty circle. And what's the slope of the bottom line? The bottom one is 2, but the top one had a slope of 1. So this next line we're going to draw is just steeper, right? Over 1, up 2, something like that. Okay? So it comes in a slope of 1, then gets a little bit steeper at that one spot. What's the non-differentiable spot here? Is it 3? What's the problem? It is continuous. It's the corner. It's the sharpness at that one spot that's the issue. Yeah, so this one is x. Yeah, it's got to be a smooth. Yeah, continuous means you can draw it without picking up your pencil, which we can, but it's not smooth. If it's curvy, no problem. Okay, so x equals 3 is the issue there. That's the corner. Okay, and just a couple of phrases here to start using this new language. You can say that a function is differentiable at x equals 2, or you could shorten that up and just say it's differentiable at 2. What that means is if we say differentiable at 2, we're telling you the x value. We almost always focus on the x's. The y's just don't really get much attention. If a function is differentiable on all the points in an interval, then you can say it's differentiable on, and then the intervals say 0, 5, okay? And then many functions we encounter will be differentiable everywhere, meaning for all values of x, and we'll just shorten that and say differentiable. So if I say a function is differentiable, I mean at every single value of x. Good?
What is the service point?
Oh, good question. If and only if, I guess, is the technical meaning, but it just means equivalent. The phrase in the front is equivalent to the phrase in the back. Okay, so what you are going to do is go back to wherever you were on this problem here. I think a lot of us were working on this one or finishing it up. You're going to do everything that's on this page. Some of us should be borrowing a graphing calculator from me for this. I want us to really know how to use a graphing calculator here. I've got the bag on the table. You can trade me your phone for my calculator for the rest of class. Once you finish this, you are going a few pages down the road to the other group activity. Don't go back to the 2 problems we skipped. Go forward, always forward here. So finish this page, come borrow a calculator, and then move forward to the page that's projected.